Hi everyone. In this video, we will be covering the second part of Chapter 8, which covers two-sample hypothesis testing. As a brief reminder, there are several ways that we can use sample data to estimate population parameters. In Chapter 7, we discussed how we can use confidence intervals to tell us whether a population parameter, whether that's a mean or a proportion, lies within a certain range of values. In Part 1 of Chapter 8, we discussed how we can use one-sample hypothesis testing as an inferential statistical test that uses sample data to evaluate the probability of a hypothesis about a population. We're going to be doing the same thing today, so still focusing on hypothesis testing, but with respect to two-sample tests. In the Chapter 8 Part 1 video, we covered one-sample hypothesis testing, which is where we tested if the mean or proportion of a group is different from the larger population. So essentially, it was group 1 versus the entire population. Now we're going to be shifting over to two-sample hypothesis testing, which is where we're going to test if the means or proportions of two different groups are different from each other. And so now we're shifting away from the idea of one group versus the entire population to two specific groups, and we can measure whether there's differences between them or not. So for a two-sample hypothesis test, this is where we're essentially testing if the means or proportions of two different groups are different from each other. So again, shifting away from the idea of group 1 versus a population to now just two distinct groups. An example of a research question that we can keep in mind here is, do teenagers and senior citizens have different probabilities of being victimized, right? This is two specific groups, teenagers and senior citizens. In the Chapter 8 Part 1 video, we saw this example used as well, but group 1 was senior citizens, but we had that versus the entire population. So hopefully this helps you visualize that shift. Now we're specifically comparing two groups to each other. Before we dive into conducting two-sample hypothesis tests, I want to just briefly remind you of the specific statistical notation that we will be using, because this will vary depending on whether we are using means or proportions. So just keep in mind this slide as a reference as we move forward. Same goes for the language that we use in hypothesis testing. This isn't a change from what you saw in the Part 1 video, so I won't spend a lot of time here, but just as a brief reminder, our null hypothesis is our statement of no difference, meaning that there is no effect in the population. So we use certain language such as no effect or no difference, no relationship, or no change. And statistically, we note this by using the equal sign. Whereas with the alternative hypothesis or the research hypothesis, this is where we state if there is an effect within the population. So you'll see language used such as an effect, or a difference, a relationship, or a change. If our problem directs us that there is a difference between our sample and another sample, then we will be using the not equal to sign, because that indicates to us that we care about both ends of the distribution. If our problem specifically states that we are interested in whether one group is lower or higher than the other group, then we will be using the greater than and less than signs listed here. As one last reminder, there are 5 general steps of hypothesis testing. Now, this is the exact same slide you saw in the Part 1 video, so just as a brief reminder before we go into our two-sample tests, the very first step of our 5-step model is to make assumptions. Now, this is going to look a little bit different for two-sample testing, but we'll get there in just a minute. The second step is to state our hypotheses, both the null and research hypothesis, as well as selecting our alpha level. The third is to select our sampling distribution. The fourth step is to compute our actual test statistic. And lastly, that's where we can make a decision with all the information we gathered through steps 1 through 4 and interpret our results. In other words, are we going to reject the null or fail to reject the null? Step 1 in a two-sample hypothesis test is to make assumptions. But this is where you'll see the assumptions vary a little bit more from what we saw in the one-sample test, mostly so that we can accommodate the new group rather than having the population. So the very first one is that we are working with independent random samples. The key word here is independent, meaning that neither of these groups can overlap from one another. They have to be mutually exclusive. You can assume that any problem I am going to give you, we will be working with independent random samples, but if you were ever to see a real world example of this in which it was assumed that the two groups had overlapping characteristics or individuals, this assumption would be violated and we could not continue with conducting a hypothesis test. The second is that the variable we are testing is interval ratio if we are dealing with sample means, or nominal if we are dealing with sample proportions. This is the same concept that we had with our one sample test, so no change there. Step 3, a little bit different for us. Because N1, which is our sample size of our first group, and N2 would also be over 50, the sampling distribution will be normal. So we have to make sure, again, that both of our groups have a sample size of over 50 for us to proceed. Lastly, this is our brand new one here. The population variances are equal if we are dealing with a two-sample test of means. So this one is specific to means only. You will be not using this fourth assumption if you are conducting a test for proportions. So again, note this down, that this fourth one is for means only. The population variances are equal is essentially stating that the normal distribution is in play here. Basically, because if we get a big enough sample size, our distribution is going to be normal, so then our variances are going to be equal as a result of that. So just keep that in mind as we're working through the remainder of the examples in this presentation. The second step is to state our hypotheses for the two-sample test. This will look a little bit different just because of the language that changes between a one-sample to a two-sample test, but we'll get there in just a second. As a brief reminder, our null hypothesis, notated by H0, is our statement that there is no effect or no difference, and it serves as the default or starting assumption that the parameter of interest in the population is equal to a specific value. So that's why we always use that equal sign when we statistically note that. In a two-sample test, the null hypothesis is a statement of no difference between group 1 and group 2. So that's where we change here as well, because before we only had one group versus the entire population. So now we're saying that there's no difference between these two groups. So let's take a look at an example of how we would actually establish a null hypothesis in the context of a two-sample hypothesis test. With our example here, we want to test whether there is a difference in the average number of crimes committed in two different neighborhoods. I see the word average here, so we're using an example for means just for the purposes of creating this null hypothesis. How we would go about stating this, both in terms of the actual verbiage, but also the statistical notation, are listed here. So we could say the average number of crimes committed in neighborhood A, maybe we select that as St. Charles here, is equal to the average number of crimes committed in neighborhood B, which we could list as St. Louis. So the way we would go about noting this statistically is what you see here at the bottom, and there's two different ways that you can go about it. I typically use this first option, but both are perfectly fine to use. The first one is stating that our population means are equal between the two groups. And the way that we designate each group is just with the numbers 1 and 2. So what we're essentially saying here is that our average number of crimes committed in St. Charles is going to be the same as the average number of crimes committed in St. Louis. Again, this is our statement of no difference. We go into the hypothesis test assuming via the null that there would not be a difference here, which is why you see the equal sign. The second component here is basically just another way to state it. I don't like it as much, but your book uses it, and so if you see it, just know that it is the same and feel free to use it if you're more comfortable. But what it's stating here is that the average of group 1, if we were to subtract that from the average of group 2, would equal 0. Reason being is that if they're equal, so let's say the average number of crimes committed in St. Charles was 1,000 crimes, and the average in St. Louis was 1,000 crimes. They're essentially equal, right? That's why I use this first one, because you could just say 1,000 equals 1,000. But we could also say that that average from St. Charles of 1,000 crimes minus the average of 1,000 crimes from St. Louis equals 0. Our second component of step 2 is to state our research hypothesis, also known as the alternative hypothesis. And these are the two ways you can statistically note that, either with H with a subscript of A or H1. This is our statement that two groups are different from each other. So again, not just one group versus a population, but that the two groups themselves are different. In this case, let's think back to the example we just used with St. Charles and St. Louis crime rates from the previous slide. What we're essentially doing there is stating that they would not be equal in this case, or maybe we were interested in whether or not the crime rates in St. Louis were greater than St. Charles or less than. That's where our symbols here below come into play. We can use a not equal sign for difference. We can use a greater than sign if we think one would be higher than the other, and a less than sign if we think that one group might be lower than the other. And so just keep that in mind. I include both statistical notations here for both means and proportions, but in practice, you will only be using either mu or pi. So just keep that in mind. You'll never actually see this written out like this. I just have it to signify that we could be using either proportions or means. Step 2 is to select our alpha level. So again, this is the probability or our cutoff point, which is going to establish our critical regions within our distribution. We usually want pretty strong evidence to reject our null hypothesis, so we usually choose pretty small alpha values. As you saw from our part 1 video, the most common 3 that we will be using are 0.1, 0.05, and 0.01. So just keep those in mind as we work through the examples a little bit later on in this video. Step 3 is where we select our sampling distribution and specify our test statistic. For a 2-sample test, the sampling distribution is the difference between sample means, so mu1 minus mu2, or sample proportions, pi1 minus pi2. So again, just keep in mind those different statistical notations there. We're using means with mu and pi with proportions. So now that we've covered one sample hypothesis testing in the previous video and had a little bit of an introduction here into 2-sample hypothesis testing, I want to take a moment to pause before we dive into our examples regarding 2-sample hypothesis testing. As a reminder, within the context of any type of hypothesis test, you will need to determine for yourself whether you are using a 1-sample or 2-sample test, as well as whether you are using means or proportions. Up until this point, and in both of these lecture videos, I will be instructing you what we're going to be doing in terms of our examples, whether it's a 1-sample test for proportions, a 1-sample test for means, a 2-sample test for means, or a 2-sample test for proportions. But on a problem set or a quiz, you will have to determine which of those 4 you will be conducting yourself. And so with that in mind, part of this pause is so that we can discuss how you would be able to identify that yourself. So the difference between the 1-sample and 2-sample tests is really just asking yourself, am I comparing one group to a population or 2 groups to each other? And that's going to come from the context of the problem itself. So there's not a clear example for me to go over, but what you can do is take the opportunity in the problem sets to practice this very thing. Am I using 1-sample or 2-sample? And am I using means or proportions? We had a little bit of practice of that in part 1, where we talked about the different identifiers between means and proportions. Oftentimes with means, we see words such as averages, and with proportions, we see actual numerical text, whether that's one value over another value, a proportion actually listed, or perhaps a percentage. And so those are 2 key ways that you can identify that. So step 1 of these 2 decision points is to establish whether or not you are conducting a 1-sample or 2-sample test and whether or not you're using means or proportions. So essentially your first decision point is, what type of test am I conducting? After you establish what type of test you are going to conduct, your second decision point is to establish whether or not you will be conducting a one-tailed or two-tailed test. And the way you go about that is also by looking at the problem itself. The key to establishing whether or not you are going to be using a two-tailed test is if you see the word difference. Oftentimes, that's our indicator that on our standard normal curve, we are interested in both ends of the distribution, or we don't care if one's higher or lower than the other, right? It could be either. Maybe we don't know in the hypothesis itself, so that's why we're saying, I'm just interested in if it's different, either from two groups to each other or from one group to an entire population. To establish a one-tailed test, that's usually where you see language about a greater than or a less than or lower than versus higher than. You're looking for an actual direction, whether that's positive or negative. And that direction itself will tell you what end of the distribution we're interested in. So if you see something with the language of lower than, you will be on the negative end of the distribution here. If you see something with language such as greater than or higher than or something along those lines, you will only be concerned with the right end or the positive distribution. So keep these two decision points in mind as you go about conducting these tests for yourself in both problem sets and on quizzes. These are two questions you should be asking yourself before you even proceed with conducting the rest of your analyses. Diving back into our steps of hypothesis testing, this chart should look very familiar to you as well. You also use it for two sample hypothesis tests. These are merely our alpha cutoff points and the associated values with whether or not we're conducting that one-tailed or two-tailed test. So these come directly from our standard normal table. Keep this chart as a reference, and it's the same one that you saw in part 1 of chapter 8. Step 4 is where we will compute our test statistic. Similar to one sample hypothesis testing, the formulas are going to look different depending if we're using means or proportions. And so when we're just going over these formulas to begin with, just keep that in mind. I think it'll make a little bit more sense when you see it used in an example, so just hang on for a few more slides. Starting off with our test statistic for means. Z obtained. Now keep in mind we're dealing with two different groups, so you won't see the same sort of symbols that you saw in the part 1 video that dealt with populations because we're no longer using them. Instead, you'll see these new notations here of subscripts of 1 and 2. What those are showing here are the sample means for both groups 1 and groups 2. And so just keep that in mind, same as we go for the population standard deviations for groups 1 and 2, same notation here at the bottom, and sample sizes for each respective group, and so 1 and 2 as well. How we plug these in is we take the sample mean for group 1 and subtract that by the sample mean of group 2. The denominator is the square root of the population standard deviations of group 1 squared, so keep that in mind here, divided by our sample size of group 1. Then we add that to the population standard deviation for group 2, which is what we have here, that's designating group 2, squared, divided by that sample size for group 2. And so this looks really daunting. I understand that. This isn't a fun formula to look at by any stretch. But again, I think once we see an example of it, it'll make a little bit more sense. In terms of the test statistic for a two-sample test for proportions, this should look a little bit more familiar to us, at least in terms of the information that we'll be using. P1 represents the proportion value of group 1. P2 will serve as the value for the proportion of group 2. The only other information that we need are the sample sizes for each respective group. And so N1 will designate the sample size for group 1, and N2 will designate the sample size for group 2. In our numerator, we see that we are taking the proportion of group 1 and subtracting that by the proportion of group 2. In our denominator, we see the square root symbol here, so keep that in mind as one of your final steps. We have P1 back here for the proportion of group 1, multiplied by a factor of 1 minus the proportion of group 1, divided by the sample size for that group. We are then going to add that to the proportion of group 2 multiplied by the factor of 1 minus that same proportion, divided by our sample size for group 2. And again, square root is your very last step there. Our last step is to make a decision. So this is where we can compare our Z obtained value, which serves as our test statistic, to the Z critical cutoff point, and we can make our decision. Are we going to reject the null hypothesis if our Z obtained falls beyond our critical value? If we fail to reject the null hypothesis, this occurs if our Z obtained is not beyond our Z critical value, and so we would fail to reject it. It's in our safety zone. Let's work through an example of a 2-sample test for proportions. Again, even though I'm specifically telling you what type of test we're conducting here, I will not be telling you that on a problem set or a quiz. And so that's what we talked about with those decision points earlier in terms of if you're conducting a 1-sample or 2-sample, means or proportions, and 1-tail or 2-tail, because that's what will indicate to you which type of hypothesis test you should be conducting. But again, for the sake of us just going over these examples, this one is specifically a 2-sample test for proportions. So let's read this question together. In the St. Charles juvenile justice system, youth are placed either in a traditional lockup facility or in a treatment program. After tracking a sample of youth for 3 years post-release, we found that 27 out of 78 youth from the lockup facility and 13 out of 54 youth from the treatment program were rearrested during this period. So essentially, they recidivated. At an alpha of 0.1 significance level, is the proportion of youth rearrested significantly higher in the lockup facility compared to the treatment program? And so I think this one is a really good example of how a researcher would actually approach this research question and try and answer this question. Policymakers might be interested in whether or not a treatment program is actually effective. And so things like this, where we can calculate how many people recidivate or get rearrested, can help people measure that effectiveness. If it is effective, that might tell policymakers that it works, right? And we might establish more treatment programs as a result. And so again, I think this is a really good real-world example of how we could actually test a program. In order to start off our hypothesis test, we always have to make sure that we are meeting our assumptions and our test requirements. So for a 2-sample test for proportions, we assume that we are working with independent random samples. So in this case, either a youth went to a traditional lockup facility or they went to a treatment program. So they are independent of one another, and we can assume that they're random unless told otherwise. So we can go ahead and check this one off. The second one is that the variable we are testing for is nominal, and this one is specific to proportions. Same if you were doing a 1-sample test for proportions. Proportions, we are always using that level of measurement of nominal. And in this case, it is because there's only 2 options. Either they went to treatment or they were in a lockup facility. There's no way for us to rank that either way or to quantify it, so that's why it's a nominal level variable. So we can go ahead and check this one off as well. And lastly, we just need to ensure that each respective group has a sample size of over 50. And from the example, we know that it is, so we have satisfied this assumption as well. Our second step is to state our null and research hypotheses. And this is going to look a little bit different from our part 1 example about 1-sample hypothesis testing. So let's discuss this a little bit further. What remains consistent is our statistical notation for both our null and research hypotheses. So we have H0 here for null, H1 designating our research hypothesis. You can also have this as HA if you prefer. But let's talk about our symbols and our statistical notation here. First, we have the pi symbol because we are dealing with proportions. So that would remain consistent if we are doing either a 1-sample proportion test or a 2-sample proportion test, so that's fine. But the change here has to deal with our subscript. So now our subscript is designating each respective group. And so what this is stating is that this is the proportion for group 1 is equal to the proportion of group 2. And so we're not comparing anything to a population in this point. And so that's why you see those subscripts enter here, because it's going to designate specifically what the proportion value is for each group. Here, this is where we have to be a little bit more mindful with respect to our research hypothesis. And so we're still using the same language regarding groups 1 and groups 2 in terms of their overall proportion value, but we also have to be mindful of which group is which, because that's going to determine which side our symbol is going. And so if it's a greater than, less than, or no difference symbol. In this case, the problem is asking us to measure whether the proportion of youth rearrested from lockup facilities is greater than the proportion rearrested from a treatment program. And so because of that, I have group 1 marked as the youth from the traditional lockup. So we expect them to be greater than that. And so that's why we have the greater than symbol listed here. And so the proportion from group 2 is listed here. So another way to think about this is that we would expect this number to be lower than this one. And so that's why it essentially has to eat the greater number. That's an old trick I have all the way back from like elementary or middle school about the direction of greater than or less than signs. So feel free to use it if you want. Overall takeaway from that, though, is just to be mindful of what group is going to be less than, greater than, or different from one another. Step 3 is where we select our sampling distribution and specify our test statistic. Now that we are specifically dealing with 2 sample hypothesis tests for proportions, we know that we will be conducting a z-test, and we've also verified that we are using a nominal level variable. As another component of step 3, we need to establish our z-critical cutoff points. We know from the context of the problem that we are instructed to use a 0.1 alpha level, and also that we have a one-tailed test. Reason being is that the language from the problem itself indicated to us that we are interested in whether or not the proportion of youth from the traditional facility had a greater rearrest rate than the proportion of youth from the treatment facility. So that's why we're interested in the upper tail here, and the corresponding z cutoff value is 1.29. Here's what it looks like visually written out. Again, I find this super helpful. If you do too, I encourage you to kind of map this out for yourself. Again, our alpha level of 0.1, a one-tailed test, and our z critical value, or our boundary of our danger zone and rejection zone, is 1.29. Step 4 is where we can compute our test statistic for our 2 sample proportions. Here is the corresponding formula that we will be using. And based on the problem, we know that the proportion of group 1, or the number of youths that were rearrested after they were released, was 27 out of 78. And because of that, we know that it has a corresponding proportion value of 0.346. I got that simply by dividing 27 by the sample size of 78 in that respective group to get that number. Group 2, or proportion 2, are those individuals in our treatment facility. Only 13 out of 54 were rearrested after they left that facility, and so that corresponds to a proportion value of 0.241. Again, I got that simply by taking the number of youths that had been rearrested, which was 13, and divided that by our sample size of 54 to get the value of 0.241. Lastly, all we need to know for this is the respective sample sizes for each group. I have 78 for group 1 and 54 for group 2, and so we can go ahead and plug in the information. Here's what it looks like with our P1, P2, N1, and N2 plugged in. So I haven't done any of the math here. What you'll see on this slide and the next slide is me working through all of the math to compute this test statistic. So this is a way for you to check yourself if you're doing this while doing a problem set or a quiz at the same time. I'm not going to go through all individual steps of the order of operations for how to ultimately find it, but double check yourself here that you have actually plugged in the correct information where it should be, and we should get to the same answer, which is on the next slide. If you worked through all of the math correctly, this is a good way for you to check yourself. You should arrive at a z obtained value of 1.324. So now we can make a decision and interpret our results. Here I have charted out both our z critical and our z obtained values. So our cutoff point that we established in step 3 was 1.29, but I know that my obtained value is greater than that. It was 1.324. And because of that, we did fall within our critical region as established by our alpha value of 0.1 for a one-tailed test. So how do we actually interpret this within the context of the problem? Similar to how you saw in the part 1 video, this shell format of how to interpret these results remains fairly consistent. So given that our z obtained value of 1.324 falls beyond our z critical region of 1.29, again, this falls beyond language means that it actually fell into this, we reject H0, which is our null hypothesis, and conclude that the proportion of youth arrested who were in the traditional lockup facility is significantly greater than the youth who were in the treatment facility. So going back all the way to the problem itself, I had mentioned that this is a really good use of a real-world example, where you could test recidivism rates between two groups to determine if something works. And in this case, it appears that the treatment facility was effective in lowering the overall amount of arrests after the youths actually left them. Now let's get into an example of how to conduct a two-sample hypothesis test for means. A criminologist is evaluating whether two federal judicial districts impose different average prison sentences for individuals convicted of drug trafficking. The U.S. Sentencing Commission has long-term administrative data on sentence lengths and has established population standard deviations for each respective district. Is there a significant difference between the average sentence lengths for drug trafficking between District 1 and District 2 at an alpha level of 0.05? And so the criminologist reported the following information here on our chart on the right-hand side. And so that's what we'll keep in mind as we conduct our actual test statistic a little bit later on in step 4. Our second step is to state our assumptions and ensure that we are meeting our test requirements. This looks a little bit different now that we're using both a two-sample test and for means, so I want you to pay a little bit more close attention to this particular slide. First, we are working with independent random samples. We can check this one off right away because each district is independent from one another. The second is that the variable we are testing is interval ratio. So this is specific to sample means. It would be a nominal level variable if we were dealing with proportions. We can check this one off as well because we are dealing with sentence lengths, and so that can be measured in either months or years, and either of those are interval ratio in matter. The third step is because our sample sizes exceed 50, the sampling distribution will be normal. Both of our samples from District 1 and District 2 are greater than 50, so we can check this one off as well. This last fourth assumption here is specific to a two-sample test for means. So I want you to pay attention to this step and assumption specifically. I'm going to star that right there. The population variances are equal. So we are assuming this. This is part of the normal distribution. Unless we had reasons to suspect otherwise, we can basically check this one off. But this is something we have to be mindful of, specifically for means rather than proportions. Our second step is to state our null and research hypotheses. These will look very similar to what we did in terms of format for a two-sample test for proportions. The key difference here is we've switched back to our symbol for means, which is mu. We're using the same subscripts to designate each respective group, so group 1 and group 2. We'll have District 1 be group 1 in this case, and our second group will be District 2. Again, our null hypothesis, which is designated by H0, is our statement of no difference, and so that's why we have this equal sign. And due to the specific use of the word different in our problem, we will be using the not equal to sign to designate that we think that the mean sentence length is different between District 1 and District 2. Again, the language may vary on other examples you may see, so be mindful of that as you're working through these. Step 3 is to select our sampling distribution and specify our test statistic. We are working with a two-sample hypothesis test for means. We also double-check that we are, in fact, using an interval ratio level variable, and so we can go ahead and proceed with our z-test. The second component of step 3 deals with our alpha cutoff value. We were instructed to use an alpha level of 0.05. We also know that we are using a two-tailed test. Again, think back to just the slide we had before. The term was different, so we don't care about which end of the distribution we're on. Perhaps we don't know if District 1 is going to be greater than District 2, or we don't know if District 1 is going to be less than District 2. And so what this type of hypothesis allows us to do by just implying the word different allows for both outcomes to happen. The associated cutoff value for an alpha level of 0.05 with a two-tailed test is positive and negative 1.96. So that's what we'll be using as we get to our decision point in step 5. Here's what this example looks like plotted out relative to our normal distribution. Our Z critical cutoff points are going to be negative 1.96 and positive 1.96 respectively. Keep in mind that dealing with a two-tailed test is going to change the area of our alpha regions because we have to divide that by 2. So each respective side is going to be 0.025 or 2.5%. Based on the problem, we know the following information, and this is what we'll need to plug into our formula in order to determine our test statistic. We know that the average sentence length in District 1 is 62.3 months. The average sentence length in District 2 was 58.1 months. The population standard deviation for District 1 was 14 months. The population standard deviation for District 2 was 13.1 months. And then we just have a little bit of a difference here in terms of our sample size. The sample size from District 1 was 100, and the sample size from District 2 was 120. So with the information that we gathered based from the problem on the previous slide, we can now plug all of this in. I've recopied over here the formula that we will be using for a two-sample hypothesis test for means. And so all we have to do is plug in all that information we had from the previous slide. Here's what it looks like if you were to plug it in correctly. So this is a good way to check yourself before diving into the rest of the calculations. What I'm going to show you on the next 2 slides is me working through the math itself. So I'm not going to spend a whole lot of time on it, but it'll allow you to check your math along the way. So here's where you should be at working through the initial phases of the orders of operation. And this is where you should get if you were to calculate your Z obtained correctly. You should get at a final value of approximately 2.28. So now that we've calculated our test statistic and our Z obtained in step 4, we can now make our decision and interpret our results. This is where we can compare our Z critical value that we established in step 3 to our Z obtained or our test statistic, which is what we just figured out in step 4. So what conclusion do we make? Again, I always find it helpful to chart this out. Our respective cutoff regions are negative 1.96 here on the negative end of our distribution and positive 1.96 in terms of the positive end of our distribution. Our Z obtained ends up being 2.28. And because of that, we do fall into our rejection zone of our null hypothesis here. And so what implications does this have for our actual problem? So given that our Z obtained value of 2.28 falls into our Z critical region of 1.96, again, we're in this shaded region here on the positive end of our distribution, we reject our null hypothesis and conclude that the average sentence lengths for drug trafficking between District 1 and District 2 are significantly different from each other. So again, we are essentially affirming what we had in our research hypothesis. Okay, you've made it to the final slide of part 2 of our chapter 8 lecture. So there wasn't a whole lot of new information in this respective video in terms of the logic of hypothesis testing or our 5-step model, but what we did do is clarify some of the unique differences between 1-sample and 2-sample hypothesis testing, as well as the different implications that conducting a test for both means and proportions may have on our test statistic. So with that in mind, just ensure that you know each of these respective steps of our 5-step model keeping in mind that there are a couple different key assumptions in two sample tests that do vary from one sample test, as well as whether or not we are conducting proportions or means, so keep that in mind as well. I realize that this is a lot of new information being thrown at you at once, and so feel free to rewatch this video at any point. I actually encourage you to work through your problem set with these examples in mind. And so with that being said, as always, if you have any questions, feel free to reach out, attend my office hours, schedule an appointment with me, and I will see you in the next video.